Welcome back, where we're continuing our discussion in Chapter 9, in which we're going to be looking at 9.7 now, which is a little bit of change of pace from series and testing of series to now what we call Taylor polynomials. Now, we have an idea of what a Taylor polynomial is already, we just don't know it yet, and we're going to expound upon something that we learned in Calc 1 and take it a step further. In fact, in general, we're going to take it infinitely many steps further. And so if you remember back in Calculus 1, you learned what we call the equation of the tangent line. And depending on your point and where it is at, you can find the slope of that tangent line and write the equation of that tangent line at any point, as long as you can take the derivative. Why? Because remember, the derivative tells me the slope of the tangent line. That is what the derivative is defined to be. So we see we can slide this point all along this curve. The curve I have for us is e to the x. But if we slide around, we get what we call the tangent line. And we'll write the equation of a tangent line. We'll look at that in a second. But what we're concerned with today, and just to start out with kind of a visualization of what we're going to be doing before we write some things down, is we're going to be expounding upon this and talking about, okay, that tangent line is great, and it's also what we call a linear approximation of my function, meaning if I zoom in close enough to this function, now of course in this case I have to get pretty close. If I zoom in close enough to this function at the point 0, 1, the place where I am centered, we can't tell the difference between the line, the tangent line, and the curve itself, right? You look at e to the x and this tangent line look very similar, centered at 0, 1. Of course, if we start to back out from this point, we notice that, yes, the tangent line and e to the x are not very similar at all. And it's not a good approximation outside of very close to 0, 1. And so can we make this approximation better? Well, yes, we can. What if we chose a better polynomial? Instead of a linear polynomial, what if we found a quadratic polynomial? Something that had concavity to it or curvature. Because then what we could do is we could bend that line and make it fit e to the x a little bit better, and so that it's a better approximation. And if I get closer to this point, I don't have to zoom in quite as far. And since I've bent my tangent line into now a parabola or a quadratic polynomial instead of a linear polynomial, it fits this curve a little bit better for a little bit longer time. How would I curve it correctly? Well, what I would need to do, instead of taking the slope at this point, I would take the slope at this point as well as the concavity of the function at this point and create a parabola with the same concavity at that point. That way I create a parabola that's similarly curved at this point. Zooming out though, it's still not a good approximation. We can do it better. Let's create a cubic polynomial. And so what I've done now is not only have I made the slope of the tangent line the same at this point, I've now also made the quadratic, or the second derivative, concavity, the same at this point between my function and this polynomial. And then I've also went one step further and made the third derivatives the same. And so whatever the third derivative of e to the x is at 0, 1, I've made a polynomial that has the same value for its third derivative at 0, 1 as well. We're trying to copy what's going on with e to the x for all of these derivatives and encoding that in a polynomial. Now it's a little bit better of an approximation. In fact, we can keep doing this. Go out to 5 derivatives now. And again, what you've done is you've looked at the point 0, 1. You've looked at all the first 5 derivatives of e to the x and looked at the output of those derivatives at 0, 1. You've looked at the slope of the tangent line at 0, 1, the concavity at 0, 1, the jerk at 0, 1, the fourth derivative at 0, 1, and the fifth derivative at 0, 1 for e to the x. And then you've constructed a 5th degree polynomial that has all those same values at the point 0, 1. That 5th degree polynomial I've created has the same slope at 0, 1 as e to the x. It has the same concavity at 0, 1 as e to the x. It has the same jerk at 0, 1 as e to the x. It has the same 4th derivative at 0, 1 of e to the x, and it has the same 5th derivative. And now, of course, you see where this game is going, because we can continue on higher and higher derivatives, make them agree in higher order derivatives, creating Higher degree polynomials, you notice this last one, this computer program taps out, at a 20th degree polynomial. Now we could continue farther than that, but we see the point here. This is a polynomial, a 20th degree polynomial, that at the point 0, 1, the first 20 derivatives of this polynomial at 0, 1 agree with the first 20 derivatives of e to the x at 0, 1. And I've created now a spitting image of e to the x that's not e to the x through using a polynomial. We've gotten a better and better approximation. And of course, we would continue this on forever. Now, we're not going to do that yet. We're just going to do it a finite number of times, maybe 3 or 4 times. But we're taking something we learned in Calc 1, and we're upping the game. We're taking it a step further. Instead of tangent lines, instead of first degree polynomials, second degree polynomials, quadratics. Instead of tangent lines, third degree polynomials, fourth degree polynomials. So instead of a linear approximation, a nth degree approximation. Now we could do this with really any function, ideally not a polynomial function, because then that's not exciting, but say we have sine of x. And say we look at the point 0, 0. And we look at the first derivative, right? In Calc 1, you talk about the equation of the tangent line at 0, 0. And so the slope of this line agrees with the slope of the function at 0, 0. But now let's create a higher degree polynomial. In this case, we jump to a cubic. We'll see why when we construct these polynomials. But in this case, now if we jump to a cubic, we have at 0, 0, this polynomial that I've created, this third degree polynomial, has the same tangent line, has the same concavity, and the same third derivative at 0, 0 as sine of x does. And so we see that it models sine of x very closely around 0, 0. We zoom in. In fact, we can make it better, right? We'll just go a little bit farther. 6th degree polynomial, 9th, 10th, 11th, 12th, and 13th. I'll go all the way to 20, and right now, even on the interval, looks like almost between -3 and 3, we can't see really a difference between sine and this polynomial. Now, as we zoom out, we see that there is a difference. But if we continued this on forever, we can kind of warp this polynomial, or kind of bend this polynomial to agree with sine of x, possibly everywhere. Maybe not, but possibly everywhere on the whole real line, on its entire domain. And so now, of course, becomes the question, okay, well, what's the algorithm here, right? We know how to construct tangent lines. What's the algorithm for these quadratic approximations and these cubic approximations, fourth degree polynomial approximations? And so what we're going to look at now is we are going to look at what those approximations look like. Now, I wrote the formula up there on the board, but let me share a PDF that I wrote up that is also available to you. And so in this case, I wrote it up and it looks nicer. This is the algorithm for the nth degree Taylor polynomial, Pn of x, of a function f of x centered at c. Now that center is very important. You notice, right, in the e to the x, we centered it at 0, 1, so when x was 0. And the other one, we centered it at x was 0 as well. And so the nth degree Taylor polynomial, that means I'm going to go out to the nth degree polynomial, the nth power, of a function f of x centered at c is given by the following formula. Now, this first couple values, these first couple values here, the f of c plus f prime of c over 1 factorial x minus c, that is actually just the equation of the tangent line. And so if you stop here, that is what you learned in Calc 1. That is the equation of the tangent line to your curve at c. But we're not concerned with that. We're taking it a step further. Now we're going to go and find the quadratic polynomial approximation of my function at c. And another step further. And another step further, all the way out to the nth step. And so instead of just the slope, we're going to need the concavity, the third derivative, fourth derivative, and so on of this function at a certain value at c. And then we have a very nice algorithm in which gives me that polynomial. You notice that, of course, these values, f prime of c, f double prime of c, f triple prime of c, these are just numbers. These are values, right? We're going to find them here. X minus c, these are just polynomial pieces, right? These are just polynomial terms. Your tangent line, your linear term, your quadratic term centered at C, your cubic term centered at C, your nth degree term centered at C. And then the question is, well, why do I have these 1 factorials here and 2 factorials? What's the point of that? Why do those become important in this algorithm? And I'll just explain it with the 2 factorial one. Because remember, we want the second derivative of my polynomial to be the second derivative of f, which is f double prime of c. Now, when I start taking derivatives of a polynomial, so just pretending we stopped at the second degree term for a second, if I start taking derivatives of a polynomial, remember that these are just numbers in front, the things that are circled, you use the power rule, which means you're going to need to take that 2 and bring it down when you take a derivative. Now, I don't want 2 times f double prime of c, I just want f double prime of c. And so I'm going to need to cancel that 2. Well, I have a 2 in the denominator that will do that for me. I will then also take the second derivative. Well, now there's a 1 power here, so I'm going to need to bring that 1 down, and it will cancel with the 1 in the denominator, since it's a 2 factorial. And so what I've done then is I've kind of undone the power rule. So the point of the 2 factorial in the bottom is to undo the power rule that's going to come when you take the derivative twice of a quadratic polynomial. Same thing here. For the cubic piece, you're going to need to divide by a 3 factorial, so that when you use the power rule 3 times here, when you bring down the 3, it cancels. When you bring down the 2, it cancels. When you bring down the 1, it cancels. And all you're going to be left with then is what you want, f triple prime of c, whatever this number is. And same thing, so on and so forth, all the way out to n. So the general algorithm is as follows. And so let's see this algorithm worked out. And so find the 4th degree Taylor polynomial for f of x equals e to the x centered at 0. We saw this one in the visualization, but let's actually write out what that polynomial would be. In this case, we're going to need 4 derivatives of e to the x. We're going to need the tangent, slope, the concavity, the 3rd degree, or the 3rd derivative at 0, and the 4th derivative at 0. Now, it's a nice example to start with because you learned in Calc 1 that the derivatives of e to the x are, again, always e to the x. And so what is f prime of e to the x? We learn that f prime of e to the x is, again, e to the x. And so we don't need to do much work here. This, again, is just e to the x and dot, 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 right? We don't need to worry about higher order derivatives with e to the x. This is a nice example to start with. And so even out to the 4th derivative of e to the x, 1, 2, 3, 4. Now, the standard thing to do anytime you pass 3 hash marks, you don't keep writing hash marks for derivatives, you'll just start doing superscripts in parentheses. And so you'll notice that in the symbols next to my writing is that we have a parenthesis 4 here that will denote the 4th derivative. Now remember, we're not looking for these functions, we need the values of these functions at 0. Well, we need to plug 0 into the function. E to the 0 is 1. Well, wait a minute, all the derivatives of e to the x are e to the x. And so again, e to the 0 is 1, e to the 0 is 1, e to the 0 is 1, and e to the 0 is 1. And so what we end up getting is 1 for all of these outputs. And so now we need to construct a polynomial that has 1 for its output of the function at 0, that has a slope of 1 at 0, that has a concavity of 1 at 0, that has a 3rd derivative of 1 at 0, and a 4th derivative of 1 at 0, and I will do so using this algorithm. We look back up here at the formula. My c in this case is 0, x minus c, f prime of c, everything else is prescribed, and so I'm just going to fill in what I have. So 1 plus f prime of 0, which is 1, over 1 factorial, which is 1, x minus 0 is just x, plus f double prime of 0, which is 1 again, over 2 factorial, which is 2, 2 times 1, which is 2, x squared, plus f triple prime of 0, which again was 1, over 3 factorial, which is 6, 3 times 2 times 1, x minus 0 is just x, so x cubed. And finally, plus the fourth derivative at 0, which again was 1. 4 factorial, 4 times 3 times 2 times 1 is 24. So 1 over 24. And x to the fourth. And so you look what you've created. You have just made a fourth degree polynomial that looks very much like e to the x around the point 0, 1. Not everywhere, but at the point 0, 1, this polynomial you just wrote down is very similar to e to the x. What would make it better? More terms. And if you actually continue to do this forever, we can create what we call an infinite polynomial, which is going to be in the next sections. And those infinite polynomials we'll give a name to. So we understand this process, though. We'll just start finite. And so what we'll do is we'll do a couple other examples, but for those examples, I will move to the whiteboard. So I will stop sharing my screen, and we'll do these examples written out. And so we continue now. I reminded ourselves these formulas. And so what we're going to do is we're going to continue now, and we're going to work through these examples. And we're going to do the other two examples that I had written on that PDF. And we're going to look at cosine centered at pi over 2 and ln centered at 1. So f of x equals cosine of x. C is pi over 2. That's where we're going to center our approximation. And then we'll look at ln of x as well. And so we're going to write out a certain degree polynomial. Okay, so how far do we go at this point? Is kind of, we're going to have to be told how far to go out, what degree polynomial we want. And so let's say we want the third degree Taylor polynomial. Third degree Taylor polynomial. Well, that means I'm going to need to take 3 derivatives of this function and then use this algorithm to construct this polynomial. So cosine of x is my function. We need to take out to 3 derivatives because we're going to need the tangent line slope, the concavity, and the third derivative value at pi over 2. Derivative of cosine, negative sine of x, negative cosine of x, sine of x. Now, these are not the functions I want. I'm not using the functions. I'm using the values of these functions at my center. And so I need what is f of pi over 2, what is the slope at pi over 2, what is the concavity at pi over 2, and what is the value of the third derivative at pi over 2. So I need to now take these derivatives and evaluate them at my given point. Cosine of pi over 2 is 0. Negative sine of pi over 2 is negative 1. Negative cosine of pi over 2 is 0. And sine of pi over 2 is 1. So since the constant in the second degree term is 0, that means when I write this algorithm out, I'm not going to have a quadratic term. I'm not going to have a constant. I'll only have a linear and a cubic piece. But if we follow the algorithm, what is P3 of x? It's going to be 0 plus negative 1 over 1 factorial x minus pi over 2 plus 0 over 2 factorial x minus pi over 2 squared plus 1 over 3 factorial x minus pi over 2 cubed. Now, like I said, because these terms have zeros, 0 times, they're all gone. So the only terms I'm left with are these two. And that simplifies to just negative x minus pi over 2. We'll leave it like this. Plus 1 over 6. 3 factorial is 6. X minus pi over 2 cubed. We don't need to FOIL this out, right? We can just leave it like this. This is a polynomial. It's a third degree polynomial. And this third degree polynomial looks very similar to cosine of x at pi over 2. So at the point pi over 2, comma 0, so that point on the curve of cosine of x, this polynomial looks very similar to it. It's not exactly equal to it, and the approximation is not very good outside of pi over 2, but for a little bit of time around pi over 2, this polynomial looks very close. And so let's do another example. Let's do one more, and we'll look at ln of x, right? We're going to look at some functions that aren't polynomials. So the typical thing to do is trig, exponential, and log functions. These are the other types of functions that we often deal with. And so let's look at one more. Let's look at ln of x. And let's center this at 1. And let's create the 4th degree Taylor polynomial. So that means I'm going to need out to 4 derivatives of ln of x. So f of x is ln of x. The first derivative of ln of x, the second derivative, the third derivative, as well as finally the 4th derivative. ln of x, remember, its derivative is 1 over x. Using now the power rule, negative 1 over x squared, 2 over x cubed, negative 6 over x to the 4th. 1 over x for the first derivative, x to the negative 1 becomes now negative 1x to the negative 2. Negative x to the negative 2 now becomes 2x to the negative 3. Bringing that down, negative 6x to the negative 4. Now again, these functions aren't my answer. We need to take these functions and we need to plug in 1. I want to know the value of the function at 1, the slope at 1, the concavity at 1, the third derivative at 1, and the 4th derivative at 1, because I'm going to create a polynomial with these values. F of 1, ln of 1 is 0. Plugging 1 to the first derivative, we get 1. Plugging 1 into the second derivative, negative 1. Plugging 1 into the third derivative, 2. Plugging 1 into the 4th derivative, negative 6. And so we can create now a polynomial using these numbers, following this algorithm. P4 of x would be 0 plus 1 over 1 factorial x minus 1 plus negative 1 over 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 cubed plus negative 6 over 4 factorial x minus 1 to the 4th. That's just following my algorithm, right? Everything is prescribed for me. The only thing I need to fill in is these values here, which we just found. So any Taylor polynomial centered at 1 for any function will have the same look. The only difference will be what the outputs of my derivative, second derivative, third derivative, and 4th derivative are, and that's going to change what the polynomial looks like. Now we can simplify this a little bit. There's no constant. 1 over 1 factorial is just 1. We can write this as negative 1/2 x minus 1 squared. This term, 2 over 3 factorial, reduces actually to 1/3. It's 2 over 6 or 1 over 3. Negative 6 over 4 factorial actually reduces to negative 1/4. And actually there's a pattern here. If you've caught on and you simplify this, you notice there's a pattern, negative 1 over 2 plus 1 over 3, negative 1 over 4. The next term would be 1 over 5, x minus 1 to the 5th. And then negative 1 over 6, x minus 1 to the 6th. And so in some cases, we can find patterns. And then we can extend this indefinitely if we can find that pattern. And actually, all the examples we've done with e to the x cosine with ln, there is a pattern there. So I encourage you to look back at those examples and see if you can find that pattern. Because what we're going to do next is we're going to take that, find that pattern, and extend this algorithm indefinitely and create an infinite polynomial with it. So we want to be able to find that pattern. In general, we're going to call infinite polynomial something. We will leave the name of that term for the next video. But this gives us a nice start. The idea here is taking this idea in Calc 1 of tangent lines and approximate a function set up by a linear polynomial, now higher degree polynomials, a quadratic, a cubic, a quartic, quintic polynomial. How do we do that? We have some sort of algorithm that helps me. And so that is what we talk about with Taylor polynomials, and we're not done with these types of polynomials. We will extend it indefinitely and call them something else. The only thing to add at the end of this section is just a matter of notation. So a Taylor polynomial centered at c equals 0 is called a Maclaurin polynomial. So this is just a matter of being proper in terminology. So if you ever center in a approximation at 0, we call it a Maclaurin polynomial. And so if you ever are told to write a Maclaurin polynomial, it's implied that the center is then 0. You always have to be given a center, and if they're not telling you, that's probably because they told you it was a Maclaurin polynomial, which implies the center is 0. Otherwise, you'll be given c equals 1 or c equals pi over 2. The only thing is a term. And so we write these approximations now, we extend this idea from Calc 1, and hopefully the goal would be to extend this indefinitely and to create infinite polynomials. And that will be the next section.